Okay, so welcome back to the afternoon session. And we have one talk today. This is the seminar part of the meeting. And the first speaker is Sayantan Sharma from Institute of Mathematical Sciences. And he would be talking about the fate of chiral U1 anomaly at finite temperatures in QCDs.
Thanks, Subhro, for this kind introduction. And I would like to begin by thanking Sergej and Subhro for organizing this such a nice meeting. And I would like to give my first topical lecture for this program by introducing you to some problem which is very specific to QCD, which is the non-abelian theory of strong interactions. But I would also motivate that it has many other applications in related areas in condensed matter systems also. So this is a very general topic, which is about the chiral anomaly and its role for the phase transitions as well as transport properties. So the first half of the talk will be on chiral anomaly and finite temperature QCD, and then in the later part, I will try to motivate other applications in related systems. So I would like to start describing the system, which is given by a very simple Lagrangian, which comprises of these fermion fields. And in the context of QCD thermodynamics, we discuss about 3 flavors of these fermion fields, which are labeled by these indices U, D, and S, which stands for up, down, and strange quarks. And they have masses. However, due to isospin symmetry, the up and down quarks have degenerate masses. So they are similar masses. Strange quark mass is about quite larger. It's about 140 MeV, whereas the U and D quark masses are around 5 MeV. And then we have this non-abelian term. This is the total Lagrangian of the color interactions. And this one contains the normal kinetic term as well as the 3 and 4 gauge couplings. So this is highly nonlinear equation. And this A consists of the color index. So that goes from 1 to 8 because we are interested in SU3 gauge theory. Now, when the up and down quark masses are much smaller than an intrinsic scale of the problem, which is the lambda QCD, or in our case, when we are doing finite temperature, this is the temperature of the system. Hence, this action has a very good U2 left cross U2 right symmetry. Is it almost like the light quarks are massless compared to the other scales which are relevant for this problem? Now, it's not an exact, but it's a good symmetry. Now, of course, you can write this complete gauge group into the non-singlet and singlet parts. The non-singlet part can be broken into an axial vector and vector part. And we know that this symmetry at high temperatures or very high energies, which is SU2 axial times SU2 vector, it breaks into SU2 vector at lower temperatures. So this is called the famous, it's known in the textbooks as chiral symmetry breaking. And because of this chiral symmetry, whether the singlet and the non-singlet parts of the chiral symmetry are restored at the same temperature or they happen at a different point. Of course, when we discuss about UA1 restoration, it is effective restoration because it's a chiral anomaly. It will never be restored exactly. But there are scenarios when it goes to effective restoration. And what we mean by effective restoration, I will explain to you in the later slides. So depending on whether the singlet and the non-singlet parts are restored at the same temperature or not, it affects the order of the phase transition, chiral phase transition, in the exact massless limit. So it can be second order with different critical exponents depending on the magnitude of this UA1 breaking. So that's why this problem is very interesting. And so the question that we want to ask is whether the singlet and the non-singlet subgroups of chiral symmetries get restored simultaneously. And from using the anomaly relation, we know that this UA1 charge is related to the index of the gauge fields, and hence its origin is topological. And another question that we as a lattice theorists want to address is what is the microscopic origin behind chiral symmetry breaking, and it's related to color confinement. So there are different ways to address this problem. I would like to highlight one method which is most comprehensive one, and it has less uncertainties because we understand it much better given so many years of work done on this topic. So we have to look at the spectrum of the Dirac operator, the massless Dirac operator, on these gauge ensembles that are generated using Monte Carlo lattice gauge theory algorithms. So we have dynamical gauge configurations, including the dynamical fermions, and we want to calculate the Dirac eigenvalue spectrum on this background. Now, why is it interesting? Because at 0 temperature, we know that chiral symmetry is broken, and then there is an order parameter related to this because the non-singlet part of chiral symmetry is exact, it is non-anomalous. So there is an order parameter which is the psi bar psi, or the chiral condensate, and this chiral condensate is related to the eigenvalue density of the Dirac operator. So if one looks at the eigenvalue density of the Dirac operator, the first term is given by the chiral condensate, and then there are other terms, and this was derived in the context of chiral perturbation theory, but now it has been verified on the lattice also. Yeah. It is psi left, psi right plus Hermitian conjugate. Yes, this is the order parameter because you need an order parameter which breaks the symmetry. So if the order parameter is 0 in one phase, you call it as a chiral symmetry restored phase. No, the mass terms are also having psi bar left times psi right. So for yes, sure. But the masses are much smaller than all the relevant scales of the problem. That breaking is very small. And this term actually is generated dynamically to non-perturbative effects. So even if you have exactly massless quarks, this term is finite in the chiral symmetry broken phase. That is the most interesting part. And this is a non-perturbative term. You cannot get it perturbatively to diagonal. Because we cannot say that because the degrees of freedom change. When chiral symmetry is broken, our degrees of freedoms are no longer quarks, but they are hadrons. So pions are the ones that are massless because of this. And then we get a tower of hadrons, much heavier hadrons. And this is a consequence of the chiral symmetry. And of course, in QCD, there is also color confinement, which happens simultaneously. So we never get free quarks even in this chiral symmetry broken phase. So this eigenvalue density of the Dirac operator has been derived in this form in context of chiral perturbation theory. And if one looks at the near zero modes, then one recovers the chiral condensate, which is the order parameter of this non-singlet part of chiral symmetry in terms of the eigenvalue spectrum. And this has been also well studied in the context of lattice gauge theory. And people have now well established this relation, the Banks-Kasher relation. Now, when we discuss about the effective restoration of an anomalous symmetry, then one has to be very careful because anomalous symmetry doesn't have any corresponding order parameter. So one way to address this problem is to look at the symmetries of the ground state, the bound state, and to see when these bound states become degenerate, or the correlation function corresponding to these bound states become degenerate. And that's how one sees effective restoration of symmetries. So for example, if one looks at these states, which I call label as eta, and this is given by psi bar gamma 5 psi, and this is the sigma or the scalar, which is given by psi bar psi. So when UA1 is restored, then these two correlation functions should be degenerate. Similarly, when when the non-singlet part of chiral symmetry or the SU2 part is restored, then the delta and the eta gets degenerate, and here there is isospin part index, the isospin matrix here, whereas this one doesn't have that. This is a isospin singlet, so flavor singlet object. So one can look at the properties of the bound states of different, these are called the mesons, and one can look at those properties of the correlation function of these mesons and their degeneracies as a function of temperature, and then discuss about which symmetries are restored at what temperature. So on the lattice, we of course study this integrated correlation function of these states. So these are given by the integrated 2-point correlation function corresponding to these particles, where I have discussed here a specific particle, which is the pion. The pion can be written in terms of fermion bilinears, but sandwiched between these isospin states, these isospin matrices, and it is a pseudoscalar. That's why there is a gamma 5. So there are 3 pions corresponding to these 3. These are just the Pauli matrices here. And then one can create them at one space-time point and destroy them, and then sum over or integrate over all these processes, and one gets this integrated correlation function. Now, when one writes this correlation function in terms of these fields, then one can contract these when calculating these expectation values, and then one can calculate these things in terms of a connected piece as well as a disconnected piece. So the connected piece are isotriplet ones, because they do not have disconnected pieces, whereas all the isoscalar singlet ones, they have both connected as well as disconnected pieces. So if you go back to this example, the pion is isotriplet. I have given a specific example here, but it is isotriplet. So when one calculates correlation functions of it, then this doesn't have any disconnected components. Whereas this kind of a particle, the sigma, which is a scalar, this has both disconnected as well as connected pieces. So one can write the total or the integrated correlation function of the sigma in terms of the delta, which is isospin triplet plus some disconnected piece. And similar for the particles which are pseudoscalar, one can write the eta, which is isosinglet in terms of the isotriplet states. And this minus is by convention. So this has a disconnected piece. But this disconnected piece is, of course, pseudoscalar one. Now, when the non-singlet part of SU2 is restored, then of course we expect that the sigma and the pion correlators should be degenerate, and similarly eta and delta. And this gives us a constraint that the disconnected pieces of the chiral part, this chi5, and for the scalar part should be equal. And then further we have chiral Ward identities by imposing that the chiral currents are conserved. One can derive this, that the disconnected piece, actually the disconnected chiral piece of the susceptibility is related to the topological susceptibility. However, when chiral symmetry is restored, then the disconnected piece of the scalar part is related to the topological susceptibility. And this is an identity which we also will try to see how well it is satisfied on the lattice. Now, why did I discuss these integrated correlation functions? Because these integrated correlation functions are simpler to implement on the lattice, because one can rewrite them in terms of the eigendensity and the eigenvalues of the Dirac operator, the lambda and the rho of lambda. So hence, to get an idea about how these kind of correlation functions or these differences behave, one needs to know how these eigenvalue density change as a function of temperature. Now, very little is, so I showed you the expression for, or the derivation of the eigenvalue density in the chiral perturbation theory. However, as one goes to higher and higher temperature, chiral perturbation theory breaks down, and then not much is known about the eigenvalue spectrum. Only recently people have studied analytically, but there were assumptions in these analytic studies. So the major assumption that went into all of these studies is that rho of lambda is an analytic function of lambda as well as the quark masses. And then these studies looked at, calculated the Ward identities of endpoint correlation functions of scalar and pseudoscalar currents in the chiral symmetry restored phase. And using the Ward identities, chiral Ward identities, they constrained the form of rho of lambda. And as a result of these calculations, they found out that these authors here, they found out that rho of lambda, if it goes as lambda cubed in the limit, even for finite quark masses or in the limit of quark mass going to 0, this is a necessary condition for the UA1 breaking to be invisible in these sectors, scalar and pseudoscalar sectors up to 6-point correlation functions. So the question we also want to ask is whether the eigenvalue spectrum is always an analytic function of lambda, or there can be non-analyticities inherent in the spectrum. So when we discuss about these problems on the lattice, it is a very difficult problem because on the lattice, realizing exact chiral symmetry is always very tricky because of the Nielsen-Ninomiya no-go theorem. That tells us that we cannot have ultra-local fermions with exact chiral symmetry and hermiticity all satisfied simultaneously on the lattice. We have to sacrifice one of them. So most of the cases, the chiral symmetry is broken due to some terms which is restored only in the continuum limit. However, so for example, this is one of the calculations that we did with a particular discretization of quarks, which is called the HISC. And here also the chiral symmetry is not exact on a finite lattice, and we recovered the exact continuum chiral symmetries only when we take the continuum limit. But we showed that by changing the lattice spacings, so when I write n tau equal to 6, it is a coarser lattice, and we go to higher, larger numbers, these are final lattices. We see that this chiral Ward identities are better respected in the chiral symmetry restored phase as we go to finer and finer lattices. So for example, here, this open symbols in the same color describe the disconnected piece of the chiral susceptibility, whereas this half times chi disk, sorry, and this is the correlation function on the left side of this equation. You see, if you go to very final lattices, then you don't see any difference between these two quantities in the chiral symmetry restored phase, which is this part of the spectrum. Now, in general, the eigenvalue density of the Dirac operator in finite temperature can be written in this form, where rho 0 is the intercept, and then there can be higher order terms. This is the highest order term that we can have, because that is allowed by the perturbation theory and also by the dimension, because this is a mass dimension 3 operator, so this goes as lambda cube. Now, by looking at the specific dependence of these coefficients as a function of temperature and mass and this value of the intercept, one tries to understand about the different subgroups and their effective restoration of the chiral group, symmetry group. And I would refer you to the poster by Ravi for more details. So for example, this temperature, when the chiral symmetry is broken, one sees that the eigenvalue spectrum has a finite intercept, and this intercept is related to the order parameter of the chiral symmetry. So this intercept is exactly equal to this, and the slope is also related in this form, where f pi is some form factor for the pions, and these relations have been verified, and there is a very good agreement with the chiral perturbation theory predictions for the eigenvalue spectrum, even at finite temperature, but in the chiral symmetry broken phase. Now, when we go to higher temperatures, of course, the intercept vanishes, which is a signature of the chiral symmetry restoration, that is the non-singlet part is restored, whereas all the other there is a small bump here, which appears when we go to final lattices. So if we go from 8 to 16, we are going towards finer and finer lattices or continuum limit. We see that the small bump appears here, a small peak-like structure, and then there's a linearly rising part of the spectrum. And this linearly rising part, we call it as bulk modes. So this is in the chiral symmetry restored phase, we see a small peak-like structure, which is in the continuum not an analytic function of lambda, as well as this rising part, which is a linearly rising part. So we could parameterize this coefficient from the lattice data. And if one looks at this eigenvalue spectrum by scaling it with the chiral condensate, then one sees that at temperatures where chiral symmetry is broken, there is an oscillatory pattern, which is also predicted from the chiral random matrix theory prediction. There is not a very good agreement because this chiral random matrix theory prediction is only valid at 0 temperature, whereas we are doing finite temperature, so there will be some broadening. However, the trend is very much visible here. There are oscillations, whereas if you go to the chiral symmetry restored phase, there is only one big peak here, and then there is no oscillation evident, or they are very much suppressed. So now, of course, if one looks at this disconnected piece, which is also related to this chi pi minus chi delta, which I would like to remind you, this is the observable which one uses to understand how much the UA1 is broken. This is related to the topological susceptibility. The topological susceptibility actually measures how much topological fluctuations are happening in the QCD vacuum. And this green points at the continuum extrapolated results for the topological susceptibility, whereas this red band is the continuum extrapolated result for the disconnected piece of the chiral susceptibility. And these actually match at these temperatures, which are in the chiral symmetry restored phase. So we indeed see that the continuum results for these two quantities match exactly, which we expect from chiral Ward entities. And then we see a very distinct temperature dependence. If we parameterize this topological susceptibility in terms of a polynomial which goes as t to the power minus b kind of a dependence, then this exponent here varies quite a lot when one changes the temperature. So initially there is a slower fall as a function of temperature, and then at higher temperature it falls much more faster. And this exponent is interesting because this exponent can be predicted also from a dilute gas of instantons. So by effective restoration, one means that this observable has a temperature dependence which is given by, which can be explained from a dilute gas of instantons. So we call this as a trivial breaking or effective restoration, because this dilute gas picture of instantons is valid even at asymptotically high temperatures. There's no other physics which can change the temperature dependence as we go to higher and higher temperatures. So one can study these quantities and see when the leading order temperature dependent vanishes and it goes over to the dilute gas type of a picture, and this happens at around 1.15 times Tc, where Tc is the temperature at which the non-singlet part is restored. So the main message from the lattice studies is that the non-singlet and the singlet part of chiral symmetry indeed seems to be restored at different temperatures. So this is around 1.2 times higher when the anomalous part is effectively restored. And we have tried to understand these features of the eigenvalue spectrum in terms of the topological constituents of the QCD medium. So this is not very important for the context of this talk, but this is some picture that can allow us to model this kind of chiral symmetry restoration. So when we are in a chiral symmetry broken phase, then the instantons or the topological constituents of QCD, they interact strongly, producing a very strong disorder. And that's why the physics can be described by a chiral random matrix theory. Random matrix theory is independent of the specific dynamics of the system. So there's a very good agreement that we also saw in the lattice results, only due to the fact that the interactions are so strong that the details of the interaction do not matter here. However, this 1.2 Tc, when the UA1 is also restored, then interaction becomes weaker, and then we see deviation from this chiral random matrix theory predictions. And of course, if we go to higher temperatures, higher than 1.2 Tc, which we call as a temperature at which the UA1 is restored, then the instanton behaves like a dilute gas. And that is what we define as the effective restoration of the UA1 part of the chiral symmetry. And there has been lattice studies which see or observe a jump in transport properties, like people measure electrical conductivity for the quarks in these kind of in QCD, and one interestingly observes a jump in the electrical conductivity at 1.2 Tc. And this is also the same temperature when we observe effective restoration of the anomalous part of chiral symmetry. So one of the questions that can be interesting to look at is whether this UA1 restoration coincides with the delocalization transition, which cause a visible change in the electrical conductivity. And similar observations have been seen in interacting model of electrons in a disordered potential by Boris Altschuler and his collaborators before. Now, we want to understand the nature of disorder to address these questions, and there are different ways to do that. One can look at the multifractality of the infrared Dirac eigenvectors, or look at the generalized Rényi entropies. These tells us about the structural properties of the eigenvector, and also one can look at universal level spacing fluctuations, which are a mixture between a Gaussian unitary ensemble, which is a random matrix theory ensemble, and uncorrelated matrices. So I would refer you to a poster by my student Ravi, who will be discussing more on this. But all of these, the structural properties of Dirac operator also changes as the different subgroups of chiral symmetry are restored. And that is one of the signatures by which one can also independently check whether when and at what temperatures this chiral different subgroups of chiral symmetry are restored. For example, I just show one of the plots from his poster. When one looks at the bulk modes, which are the linearly rising part of the spectrum, it shows a very good agreement with Gaussian unitary ensemble of random matrices. Whereas in this temperature range, when UA1 is not restored, then one sees these kind of intermediate modes, which has a level spacing ratios between a Gaussian unitary ensemble and an uncorrelated matrix ensemble. And the physics of it is very interesting. And these are actual signatures of the fact that UA1 is broken in this range, temperature range. And in the last few minutes, I would like to move into some other interesting topics which are related to anomaly and topology. So, we were discussing about quantum field theories where Lorentz symmetry is is intact, whereas in condensed matter systems, we know that the Lorentz symmetry is violated explicitly. However, in certain materials like wild semimetals, the Lorentz symmetry can emerge effectively at low energies, and giving rise to low energy quasiparticles which have the same dispersion relation as wild fermions in QCD. So the low energy fermions have the same dispersion relation that the wild fermions in QCD has, and they have an effective relativistic description. If one now puts the system in a parallel electric and magnetic fields, two independent of them, then the chiral current in this kind of system satisfies the anomaly relation. So here E and B are the external fields, electric and magnetic fields, which are parallel to each other. And this N actually is an integer, and it is a topological invariant at each node of a N-flavor Weyl system. For a normal Weyl semimetal, of course, N is 1 or -1. However, on a finite lattice, due to Nielsen-Ninomiya theorem, the total anomaly is 0. So this is conserved. But at each node, of course, it has a specific integer, depending on whether we are looking at N-flavor Weyl systems. Now, there are interesting systems where these two Weyl bands, they may hybridize and form some kind of a hybrid structure where one has this topological bands with linear dispersion and a flat band, which has a 0 energy, and another flat band which has a finite energy, which is unrelated to these. This is a non-topological band. And these kind of systems also have a total topological charge of +2 or -2, depending on what type of double Weyl system they started with. Now, these kind of systems has a net topological charge of +2 or -2, and they can be compensated by another such system, three band system, or can be compensated by a 2 Weyl system. So this is a symmetric realization where one compensates for the topological charge of this 3-band system by another one, such that the total chiral anomaly is 0 to respect the Nielsen-Ninomiya theorem, whereas it can be also done through this kind of a realization. And of course, these systems have effects of higher order or the higher momentum part of the band structure. So the flat band is actually not exactly flat, but it has a curvature. But near the node, of course, it is flat. And the effects of this band structure at high energies can be modeled in terms of a parameter-dependent non-abelian gauge field. So one can describe the Hamiltonian of these systems in terms of two independent Weyl Hamiltonians plus a non-abelian gauge field, which has a parameter G, which actually models or mimics the effect of the high energy parts of the band, which curves these bands as we go to higher and higher momentum. However, this presence of this parameter G doesn't change the physics of this node or the anomaly of this node. Now, in presence of these, in modeling these systems, we needed to put in this non-abelian gauge fields with this coupling here. And this, if one does the anomaly calculation in this kind of a system, then one gets, apart from a topological part, one gets a G-dependent contribution, which is a non-topological part because we can now switch, tune on G and then change this part continuously. So it is no longer a topological invariant. And this comes because of the effects of Lorentz symmetry breaking, which gives rise to this kind of a dispersion. So I would refer you to the poster by Shantanu for this topic to know more details about it and its consequences for transport properties. And then there are more exotic systems like Many of you are familiar with this topological insulators, where the conductance of the edge states are characterized by non-trivial topology of the bulk. So the Chern numbers of the bulk wave functions actually determine the conductance or Hall conductance of the topologically protected edge states. And then in the recent years, the concept of topological insulators have been extended to symmetry-protected topological states. Certain discrete symmetries actually protect it from being continuously deformed from the gapless to the gap state. Such states hence cannot be adiabatically deformed into trivial insulators without closing the bulk gap, if these discrete symmetries are not broken. So in the conventional topological insulators, the topological phases in d dimensions of the bulk are related to the d-1 topological contribution to transport properties, for example, in the d-1 dimensional boundary states. However, in these higher order topological insulators, the d-dimensional nth order topological states actually give rise to d-n dimensional boundary states, where n is of course less than d. And this makes it interesting because this is going from the original paradigm and stack all of these to get quadrupolar topological insulators. But of course, the dispersion relation, of course, this is in the context of higher order wild semi-metals. So there are, so if one looks at the phase diagram, one has this bulk modes, and then there are gapless hinge modes in this bulk, which gives rise to exotic transport properties, which is very interesting. And for more details, you can visit the poster by Harshit. So to end this talk, quantum anomalies continue to challenge our understanding about phase transitions and transport properties in different systems. In a strongly coupled system like QCD, evidences favor the scenario that the anomalous U1 part or subgroup of the two flavor chiral symmetry is not effectively restored simultaneously with its non-singlet counterpart. So different studies, different ways of looking at this problem gives us this picture now. And of course, we are working for the physical quarks. They are massless in the sense that their masses are much smaller compared to all other relevant scales of the problem. But to confirm it, we need to go to a cleaner case where the quark masses are explicitly zero in the chiral limit. But of course, this is a very difficult problem because we never reach chiral limit in a numerical calculation. And we have to look at the scaling properties and all of these things very carefully. And finite volume effects are also important in this picture. And efforts are on to connect the role of anomaly to the topological constituents of QCD. I gave you some very rough intuitive picture of it. However, this is far from being settled. So studies are going on in this regard. And recent discovery of higher order wild semi-metals provide exciting prospects to connect topology to chiral anomaly in a much less complicated system, I would say, but nevertheless extremely interesting. Thank you very much for your attention.
Questions? Okay, perhaps a very nice question from a ConMat person. I understand that in QCD, the gauge fields are dynamical, they're strongly interacting, and it seems that one of the main lines of your analysis is based on the Dirac spectrum in some ensemble of random gauge field configuration. But to which extent does this model the initial QCD problem? The connection between these two, I understand that there's a deep connection if you sort of know in the end the measure you have to take for your gauge field ensemble, but to which extent do we know the measure one has to take when you perform this averaging over the gauge ensembles?
Yeah, so the measure, we know it exactly. So when we do the Monte Carlo algorithm, we generate it with probabilities e to the power minus s. S is the total action of the QCD. So we know it very well. All of these configurations are dynamical in the sense that they're exact realization, only on a finite lattice.
So, okay, so you're taking the Young-Mills
Yes.
action for the QCD. Yes. Okay, okay, very good, thank you.
More questions?
Maybe some sort of comment. I'm very happy to see that last part of your talk. It sounds of my area of researching. Would you be kind enough give me some references when you discuss that Lorentz symmetry in wild semi-metal, chiral anomaly and Nielsen-Ninomiya theorem, and the chiral anomaly in the spin one harmonic system. And also I'm very much eager to discuss with your student Shantanu.
Yeah, sure, I will.
More questions? If not, let's thank Sayantan once more.
Thank you.
The rest of the afternoon is free, so there is poster sessions after this. At some point there would be tea outside. So people who are presenting the posters, please put up your posters aboard.